Okay, so 4.5. 4.5, once again, there's only 3 homework problems for us in 4.5. There's only 3 homework problems for us. I hate to tell you this, but these problems, I don't believe, they're not on the test or the final, but we do have to look at them and think about them for a second. So, I mean, these are, since there's only 3, but these are a little bit harder. These are a little bit harder, but we don't put these on the test. The counting rule, let's see what it says. By using the fundamental counting rule, permutation rule, and the combination rule. So we're going to try to use everything. Is that an actual question, or I think they just wanted to talk to us? So find the probability of getting 4 aces when 5 cards are drawn from an ordinary deck. So we're not just looking. So before we were in 4.4, we were looking how many different how many different ways we can do this, arrange those letters. How many different combinations, how many different permutations, you know, how many ways of arranging, how many different ways of arranging. I say that over and over again. But in this section, we're not looking for how many ways to arrange. We're looking for the probability. So this is not finding the ways of arranging, even though we're going to use that. We're finding the probability. And probability, don't forget, to calculate probability, we're looking for the probability on the bottom, the probability of everything we're talking about divided by the probability of an event. So the top is the probability of an event, or no, wait, sorry, I wrote it down wrong. The possible ways of an event divided by the total possibilities. So let's look at this problem. Find the probability of getting 4 aces when 5 cards are drawn. So we're going to draw 5 cards. We're going to draw 5 cards here. 1, 2, 3, 4, 5. This is a really crazy section. Probability of getting 4 aces when we draw 5 cards. Would you agree the total ways of getting so on the bottom, the total possibilities of me drawing 5 cards, doesn't matter what order. If you have 4 aces, does it matter what order you have them in? By the way, if I have an ace, ace, and a 2 and an ace, ace, when you're playing poker, I think they're talking about playing poker. When you play poker, does it matter what order you get your aces?
I don't think so.
No, because you can arrange them any way you want in your hand once you get your cards. So the order does not matter. So these are combinations. It's important that we know the order doesn't matter just as long as we have 4 aces. So the total possibility way of drawing 5 cards, we're going to draw 5 cards. The order doesn't matter. Out of 52 cards, do you see? We're going to take 5 cards out of 52. That's my total weight. That's my total possibility of drawing 5 cards. See, it says here, the total weight of drawing 5 cards. The top is the event. The top, we have to find out how to draw 4 aces out of those 5 cards, okay? So we need to draw 4 aces out of those 5 cards. That's the hard part. So let's do these 4 cards here. Out of if I look at if I ask you, I need to draw an ace here. It doesn't matter where I draw ace. What's the probability, or how many choices do I have of selecting an ace in this spot? I need 4 aces, and I'm going to pick it in the order doesn't matter. So do you see there's 4 aces in the deck right now? There's only 4 aces that I can choose from to put in this spot. The next one, there's 3 aces. The next one, there's 2 aces. The next one, there's 1 ace. So we picked 4 aces. 4, 3, 2, 1. My question to you is, though, what do I put in this last spot? If I have 4 choices to pick for an ace here, then I have 3 choices to pick an ace, 2 choices to pick an ace, 1 choice to pick an ace. How many choices do I have to put in this spot? Anybody know?
Wouldn't it be 0?
No, because if it's 0, it multiply. Something has to go in this spot. Do you see, I already have aces. I already have 4 aces. Does it matter if I have a 2 in here or a 7 in here or a jack in here or a queen? Do you see, it doesn't matter what card I have in there, I still have 4 aces. If I use those 4 aces up, then I only have 48 other cards that can go into that last spot. Do you see, I have 4 choices for an ace here, 3, 2, 1. Now in this last spot, I only have 48 cards left in my hand. I have 48 choices to put in this spot. I could have a 2 of hearts. I could have a 3 of spades. I could have a queen of diamonds. It doesn't matter. I have 48 other choices. I still have 4 aces already. 4 aces wins. So that's my possibilities for the event on top. My top is 4 times 3 times 2 times 1 times 48, all divided by the total possibilities of drawing 5 cards, 52C5. So this is a probability. And by the way, drawing 4 aces is a very small possibility if you play poker, if anybody's played poker before. So I'm going to, on my calculator, I'm going to make it my screen bigger. I'm going to put, since there's more stuff to do on the top, I'm going to put it in parentheses. 4 times 3 times 2 times 1 times 48, close parentheses, divided by 52C5. 52 math. C5. And if you look at that number, wow, it's very small. I get, on my calculator, I get 4.4325 E negative 4. And once again, the way this is scientific notation, 4.4325. A negative 4 means I have to make this smaller and move it the decimal 4 spots. 1, 2, 3, 4. So the probability of me getting 4 aces, and it doesn't matter what the last card is in that 5th spot, I still have 4 aces, is very small, right? The probability of me getting 4 aces is very small. That's a very small probability.
Could you shorten the aces to a factorial?
Yes, you can do 4 factorial times 48. Yes, you can. Yes, you can. All right, let's see what else we have. I'm not a big fan of the this section. Let's see. We'll do at least, how many more are there? There are a couple more. Let's see if we can do this one. A box contains 24 transistors, 4 of which are bad. If 4 are bad, that means 20 are good because we have 24 transistors, 4 which are defective. If 4 are sold at random, we're going to pick 4 at random. Find the following probability that exactly 2 are defective. So on the bottom, we're going to pick 4 at random from 24. And it doesn't matter what order we pick them because we're just picking transistors. Some are bad or some are good. So it's a combination. Order does not matter. Do you see we're picking 4 from 24 transistors? That's the total. Now, up here it says 4 of which are defective. Find the probability that exactly 2 are defective. So if this one is, oh Lord. Okay, so this one can be done actually with 2 combinations. Exactly 2 are defective. We're going to pick 2 out of 4. So the top part is, remember, the top part is our event. Our event are the number that are defective. 2 are defective. 2 are defective. 2 out of the 4 are defective. But then we still need 2 more out of the 20 that are good. So we still have to pick 4. We picked 4 on the bottom. We have to pick 4 on top. These are the defective ones, and these are the good ones. Do you see, out of good, we have 20, and we have to pick 2 from the bad and 2 from the good. 20 C2, picking 2 from the 20, and then picking 2 from the bad. So this one goes in our calculator like this. I'm not a big fan of these. So let's type in this probability. You get these really small, really off the wall probabilities. So you need a parentheses for the entire top. 4C2 for math combination 2 times 20 math combination 2 divided by 24C4, 24 math C4. Oh, that doesn't look too bad. If I typed it in correctly. Anybody else get this? That's about a 10% chance of getting exactly 2 defective. And there's a good chance I typed it in wrong. Anybody get that? If you're doing it. All right. Anybody have any comments on it? I'm gonna just use that and then I think move on. If not, I think I might be done. Let's see what else we can do here. All right, so let's look at this 53. This is our last one for the day. State lottery. In a Pennsylvania state lottery, a person selects a 3-digit number. So here's a 3-digit number, right? Like 1, 2, 3 is a 3-digit number, 123. There's a digit. By the way, how many digits can go into this first spot? Anybody know how many digits can go in that first spot?
10.
Yes, I just want to make sure everybody understands there are 10 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. There are 10 digits. So 10, 10, 10. So on the bottom, when we do probability, we're going to pick 3 from 10 digits. Now, in the lottery, a person selects a 3-digit number and repetitions are permitted. Does it matter the order? If I pick 1, 2, 3, is it the same as 3, 2, 1? Do I win $1 million? I would say not, right? I think the order matters here. For this one, I think the order matters. 120. If I pick 123, that's different from 321 in this particular case, because they're just talking about a 3-digit number. That's just talking about balls they pick out. So this is a permutation because the order matters. So this is 10P3 is on the bottom. Okay, so the question we need to ask is how many, if a winning number is selected, find the probability that we'll have all 3 digits the same. So we could have 1, 1, 1, 0, 0, 0, 2, 2, 2, 3, 3, 3, 4, 4, 4, blah, 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 to 9, 9, 9. How many ways can the digits all be the same? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Do you see there are 10 ways that all 3 digits are the same? So we just put a 10 on top of here because it says find the possibilities of getting all digits the same. Well, there are 10. You can pick 0, 0, 0, 1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4, 4, 9, 9, 9. 10, and these are all the other probabilities of the permutations down below. So in this one, we just write this down, 10 divided by 10 math probability. P is number 2, 3, and the probability is 0.01388. From my calculator.